Yeah, hello. Nice to be here to present. And I am Andreas Brännström, a quite recent PhD student here at Umeå University, Sweden. I've done this work together with Timotheus Kampik and Juan Carlos Nieves Sanchez here at the university. So our work is towards human-aware epistemic planning for promoting behavior change. And the aim of this study is to introduce computational models to deal with scenarios where an intelligent agent's task is to promote human behavior change and assist a human in reaching their goals in a human activity. We have a use case that we're focusing on here, and children with autism experiences stress in social environments. And in a virtual reality environment, they can be provided assistance through some interactive training simulations by implementing an agent into this environment that can adopt aspects of the environment to assist the child through walking through this scenario. So our research questions, by considering an agent that has control over manipulating an environment, how can the agent reason about dynamic goals in human-aware planning? And how can an environment be dynamically adapted based on the interactions with a human user in order to promote human behavior change? So we developed this virtual environment simulating a cafeteria where there are people, there are sounds and different light intensity, different things that can that these children usually have difficulties with, that can provoke stress. In this environment, we have these different areas. You walk into a lobby, you walk by the queue, pick up some food, and find a table. And the agent can do different adaptations of this environment. And they can be low or high amount of people. It could be a different level of interactions. Arrows can be shown to assist the user to know what to do. And different light intensity can be changed as well. In human-aware planning, there's a software agent situated in an environment populated by humans. And there's some plan merging going on there, where there's a human plan and an agent plan. And this is a series of actions that they need to be merged, and where the agent's plan adapts to meet the requirements of the human plan. And for this, the agent needs a way to predict human actions. So we're thinking about human-aware epistemic planning, where we use a definition from cognitive science for epistemic actions that are actions in the physical environment taken with intent to gather information or facilitating cognition. Based on this definition, our agent takes epistemic actions for adapting the environment and observing human behavioral responses. Based on these observations, the agent and a model of the human, the agent can generate plan on how to encourage human actions. We want to give the agent a kind of theory of mind of the human. Theory of mind is the ability to attribute mental states, such as beliefs, intention, desires, of another agent. By adopting this agent theory of mind, the agent can start to reason about human beliefs, desires, intentions, behavioral motivations and inhibitors. It can predict human actions and possibly promote human actions. In order to create a theory of mind for agent, we are utilizing this cognitive theory of planned behavior. It's a cognitive theory to explain and predict human behavior, where behavior intention can be predicted by the individual's attitude towards the behavior, subjective norms toward behavior, and perceived behavioral control. The theory of planned behavior, it orients from beliefs of the human, which later on is merged into the intention towards the behavior. In the theory of planned behavior, they introduce a set of equations for these three set of beliefs. The attitudes, the subjective norms, and the perceived behavior control. And these are individual beliefs within these three sets that are multiplied by the human's evaluation towards that belief. We have made a set of definitions based on these equations, and the first is attitude. And we have a set of expected outcomes of an activity, propositional atoms, and these can be quantified and multiplied with the agent's evaluation, the human's evaluation of the expected outcome. Subjective norms can be defined, where we have a set of proposition atoms that are the social influences of an activity. And we have the quantification of this social influence, and we have the agent's motivation to comply with the social influence. We can define perceived behavioral control, where we have a set of proposition atoms which are the performance aspect of an activity. We have the quantification of a performance aspect and the agent's perceived controllability of a performance aspect. We can define behavioral intention, which puts this all together. The activity, the attitude, the subjective norm, and the perceived behavioral control, together with a set of weights for this different set of beliefs. This is an example of perceived behavioral control, just to show how this formula works. So we have a set of control ability beliefs. Stand in line, go to a table, for example. These are different activities in this environment. These are quantified, and the person's perceived controllability of these different beliefs are multiplied for each belief. And these are all summed, which is the overall perceived behavior control. We introduce an action language which is based on theory of planned behavior, where we introduce a syntax and semantics based on other languages, other previous action languages. And there's an alphabet in this that consists of fluents and actions. Fluents that express property of an object in the world, and action that changes fluents in the world. And we introduce a human-aware alphabet where we incorporate these fluents and actions. a human-aware domain description language, which is based on previous description languages, and we introduce a set of expressions. An action A influences attitude fluent in an agent, influences subjective norm, influences control. And we have a set of fluents influences attitude, set of fluents influences subjective norm, and a set of fluents influences control. These are new expressions that we introduce together with expressions that exist in previous languages, like triggers, allows, and so forth. We have a system flow chart works sort of like this, that the agent observes the environment. It uses DVK planner to reason about these observations, to find a set of plans. And we call this a counterfactual instance, where the agent deliberates about these plans and find a final plan, which is executed on the environment to do adaptations. And the human may respond to this, which provoke more observations and so forth. Here are some test cases. We have a set of different observations and the planner actions, planner agents actions. So for example, this one, where the attitude is low, the subjective norm is low, and the control is high. And this is the difficulty level. So the control difficulty level is high in this case, which provokes an increase in guides from the agent and no other actions. In this scenario, the attitude stress is high, the normative stress is high, and the control stress is low. Instead, this agent's plan is to decrease sounds, decrease light, and decrease light again. There can be multiple levels of these different fluents. See where we are now. I think my time is up soon, so I will just go through this knowledge elicitation process really fast. So we interviewed a set of experts to get this knowledge on which we modeled all this these fluents and actions. We found through a thematic analysis, we found these different signs of stress, sources of stress, management of stress. And we defined knowledge graphs of the user's perspective and the environment. And from this, we defined a user model with attitude stress,
somewhere in November,
normative stress, and control stress and position. Fluents of the environment can be defined as stress-provoking fluents, normative stress-provoking fluents, control stress-provoking fluents. And then we have different attitudes, fluents that provoke stress, such as noisy sounds, other agents in the environment, relaxing music, pleasant lights, motivations. Subjective norm fluents, this concerns other agents in the environment. Perceived behavior control fluents, social interactions, tasks and decisions. These are all things that are connected to the use case of autistic children. In this, we can define tailored weights, which is connected to these different environment fluents. So the attitude weights, normative weights, and control weights. This defines the impact of different fluents on the user stress in a state. Action reasoning can be defined, preconditions, and causal effects. And a set, this is simplified, but a set of actions and causal effects can be defined, such as show guides to relieve control stress. So our contributions is the action language, CTBP, based on theory of plan behavior. And we have defined a human-aware planning architecture, action reasoning approach, using logic programming. The agent deliberates about the human behavior, generates a plan on how to adapt the environment, observe human behavioral responses. And this can be personalized by these tailored weights that is connected to the environment fluence. We plan in future to do evaluation of this architecture with usability evaluation with users, as well as formal computational evaluation. And we plan to make an online evaluation environment where anyone can explore this tool. And automated learning of these tailored weights will be explored as well. And we plan to do a full semantics of this CTPB action language. All right, thank you very much.